So yesterday the heart of our whatever we were trying to learn was about the Perron-Frobenius theorem and how we can apply it to simple graphs. So most of the graphs that we were dealing with were either the nodes on a line and so on. So in principle, you can, not in principle, it applies to any other undirected graph as well. So for example, if you have to work with a generic graph, let's say with an arbitrary degree distribution, um, let's say for example, just to again motivate through examples. So I have one simple case here. So with 5 nodes. So let's just label it as 1, 2, 4 and 5, maybe this. Okay. So I want to do a random walk on this graph, and you need to just generalize the idea of doing a random walk on a line to a more generic case where each node can have different degrees. So like we argued yesterday, let's say that if you have a walker at node 4, the way you would normally split the probabilities is by saying that from 4 the walker can go either to node number 1 or node number 3 with probability half and half. It need not necessarily be half and half, but let's say that's, if you want to divide the probabilities equally, that's one way of doing it. And if you are at, let's say, at node 3, you could go to either 1, 2 or 4 with probability 1 by 3, 1 by 3, 1 by 3. So which means that degree of the degree of the node plays an important role, which means that the transition probability I can write as P going from I to j, which I will write it as P I to j is Aij divided by Di. Di is the degree of ith node. Aij is the adjacency matrix, and Aij is 1 if I and j are connected, 0 otherwise. So the probability would otherwise be zeros for nodes that are not connected to it. Now you can write out the Markov chain for this, like we did yesterday. So you can put all the transition probabilities together in a matrix form. Let me just, since I've already written it here, just let me write it down. By now, I guess you're familiar with this way of doing things. Okay, so one thing you notice is that there are many zeros in this transition probability matrix, and you can hope that maybe if I compute some p power n for large value of n, these zeros would go away, and that is actually true in this case, because even by when you look at the graph that you have, it is irreducible and it is also periodic, simple to it's aperiodic, it's very simple to check. So it satisfies the conditions for Perron-Frobenius theorem. So in fact, I calculated it, but I don't have the thing written down here. So even if you take p to the power 4, all the zeros would vanish, and it will be a matrix where all the entries are positive definite. Now you can calculate the left eigenvector. Since we've done that yesterday, just let me write the result directly. So the left eigenvector, which I'll denote by pi, is 3 by 2 1. Now you can normalize this such that the elements sum to 1. So if you normalize this, this pi would become 3 by 14, 1 by 7. Now, just to compare what we have, let me write out the degrees of the nodes. Okay. So, the degrees of the nodes involved are 3, 3, 4, 2 and 2. So, if you go back and see the way we have labeled, so you can just write out the degrees from here. That is what I have done. And now if you, I'll just do a slight change. So I'll rewrite this normalized eigenvector slightly differently now, so that you can actually see what is happening. So 3 by 14, 3 by 14, multiply and divide by 2 in the rest of the 3 elements. So that will be like 4 by 14, 2 by 7, 2 by 7. Okay, now it's very obvious and very suggestive. So the numerator is all simply the degrees divided by some normalization factor. So if you are sort of inspired by this simple example, you would say that in this case, the invariant probability on the ith node of your graph is simply di, and did I make a mistake? Oh, multiply, okay, yeah, sorry. Okay. Yeah, so the denominator is simply twice the number of edges. So just go back and count the number of edges, it should be 7 here. So it's simply twice the number of edges. So let me write it as 2e. So this is a sort of general formula you can write for this problem, but it's actually generally true. Okay. So you can actually go back and show that this is indeed the eigen vector corresponding to any general Pij. You can choose any general transition probability matrix, provided it is irreducible and also aperiodic. The elements of the eigenvector would simply be di divided by 2e. For example, I mean, one thing you can do as a quick exercise is take this, plug it in this equation that we wrote down yesterday. So write the form for Pij, and so if I have to write this equation in component form, for example, so I would write it as pi j summed over I Pij. Okay. You can plug in the right transition probability matrix for your Pij elements. We've already written it down somewhere here. Here, this one. And you can plug in this pi I there and show that it actually satisfies. Okay. So this is basically, you've taken a simple example and essentially inspired by the result, you're trying to see if it is generally valid. But actually independent of this, you can start from first principles and prove that pi ij is equal to this di by 2e. That's possible. Okay, that's a slightly longer derivation which I'm not going to do, but you can do that. You have to start from what is called a master equation. Equation that tells you how probabilities change with time, and some manipulations are needed. You can get this exactly. Okay. So what is the, so what do we, so given that you get this, let's say this pi I is ti by 2e, what does it physically say in a network setting? So it is a quantity that kind of tells you how attractive a node is for a walker. So you can see that pi I is proportional to the degree of the node. Okay. So your pi I is proportional to degree. So it tells you that if you actually, let's say you have a large graph and put in large number of random walkers, the probability of attracting more walkers to ith node is proportional to the degree. So larger the degree, more walkers are going to come there. That's what this is telling you. And another important point which we've been emphasizing since yesterday is that this only depends on the degree of the ith node, doesn't depend on the past history of any of the random walkers, and doesn't even depend on the rest of the connectivity structure in the entire graph. Okay. So much so that if you okay, we didn't do a full derivation, but even if you derive it fully, you wouldn't have to really take any information about the connectivity structure of the larger graph. That doesn't go in here. So which means that this quantity di by 2e is actually independent of the particular structure of the graph. So it's valid. You can use this even for random walks on a line. You can use this for random walks on a ring, absorbing boundary conditions, or even for more complicated undirected graphs. So again, in the exercise that I had given, I had left it as an exercise for you to verify this through simulations. So this is typically called the occupation probability, at least in physics literature. Simply because it tells you what is the, you've been running random walk for a very long time in your graph. You want to ask the question, what is the probability that a particular node has been occupied at all? And that is simply this number. So there are two ways when you want to do a simulation of this. There are two ways. You take one walker on a large graph, keep doing the random walk, and let's say you simulate it for let's say maybe 10 power 4 time steps. Okay. So you ask the question, how many times out of those 10 power 4 time steps the walker actually stepped on to the node of your interest, ith node. So that number divided by this total will give you the probability. So the longer you do it is better. So it should agree with this number, di by 2e. So typically, this is just doing with one random walker, but ideally what you should do is launch large number of random walkers at the same time. Since these are all uncorrelated processes, it's more easier to deal with large number of random walkers, and you will get a better averaging to get this result. Okay. Okay, so underlying this is again Perron-Frobenius theorem that we met yesterday. So in fact, you can also use this as one of the centrality measures. So the eigenvector centrality measure basically depends on this. I wanted to say more about it, but I am obviously running out of time. So we'll go to the other centrality measure, which is more popular and useful in the web search context. That is the page rank itself. I'll spare you this this one. Okay, since we've gone through a whole lot of random walk, the first thing is, at least from our perspective, you can think of calculating page rank as doing a random walk on a directed network. So here the setting is you have the web graph. Web graph meaning, I guess all of you know what the web graph is. Simply the graph that is constructed by following the links of the web pages, for example. And you want to know which are the important ones for a particular search query. That is a problem to be solved. And the central idea here, the core idea here is that a page is important if it is pointed to by other pages. Meaning that if you maintain a web page and many others are giving a link to it in their web pages, then possibly your web page is somewhat important. But then it is a circular argument because it's like a chicken and egg problem. You are important because other important people say that you are important. So if you look at the top equation there, this R of Pi denotes the page rank of ith page, and this modulus of Pi is the number of outgoing links. Okay. So it's like links which goes to some other this one. So if you the reason for dividing it by PI is that, let's say I'm someone, I'm going to hand out all these incoming links to all the others. If I keep handing out more and more, I actually lose importance. So like when we write recommendation letters, you simply say everyone are amazing and great, then it loses its value, such superlative expressions. So it's exactly to capture that idea that you can't keep handing out too many of such incoming links to others. Okay. Okay, so now you can treat it like a random walk. So it's essentially, you can think of a random surfer, meaning someone who starts from a web page and randomly chooses one link from there, goes to some other web page, again randomly chooses another web page from there, and keeps doing this. Occasionally, the surfer gets bored with this process and then randomly starts off again and keeps doing this again and again. So essentially, it's like a slightly modified form of the standard random walk process. So you start initially with giving equal weightage or equal page rank to all the web pages and start iterating this equation. And this, you can write it in the form that we are more familiar with, where this matrix H is called the hyperlink matrix. So this is exactly similar to the transition probability matrix that we have. Just notation is different, but otherwise it's similar to that. And again, you can see from the notation that pi that we are after is simply the invariant probability vector. And what do we expect of this equation? We want this vector to converge. So let's say that if you had n number of web pages that you are going to deal with, then this matrix H will be of order n by n. Today on the web page there are probably billions of web pages, so you are really dealing with a large transition probability matrix. What is? So this is a summation over the the neighborhood of the particular nodes. So you can only like go to a node to which the links exist. Yeah, right. So there are two problems with this straightforward formulation that looks very similar to what we have been doing since yesterday. So we want this page rank vector, which is simply the invariant probability distribution, to converge. But there are two problems. So if I look at this very simple graph of 6 nodes and some directed edges, first thing is that there are dangling nodes, in the sense that, like for example here, you see that entire second row 0, simply because once a walker gets into node 2, the walker cannot come out of it. Okay, so that is a dangling node. So there's a way to go in, but there's no way to come out of it, and that creates problem. If you have an entire row of zeros and many such rows, that is a recipe for a problem. You can't directly apply Perron-Frobenius in that case. So that is one issue. So when you get to that problem, the solution suggested by the inventors of PageRank algorithm, so Larry Page and Sergey Brin, is that you simply replace it by a equal probability, which is equivalent to saying that when you are in that situation where you are at a dead end, simply go and start off afresh with equal probability anywhere. Okay. So you replace that entire row of zeros by 1 by 6. So that's written in equation form below. That is what is called the stochasticity adjustment technically. Second problem is of course irreducibility. In the sense that there is no guarantee that a very large graph like this is going to be irreducible. Especially you know that there are dead ends and there could be several communication classes the way that we discussed yesterday. So it's a problem that there is no guarantee that a path will exist from every node to every other node in that large graph. Okay. So the solution to the second problem is that occasionally you simply teleport to a new site with the equal a priori probability. So which means that you have this matrix S. So you will use that transition probability matrix yes until you keep following the links, but every now and then the way you say that you get bored of following the links, so you simply teleport to a arbitrarily new new website and keep doing the same thing again. Okay. So that is controlled by this parameter alpha. So there is a probability for following the links, there is a probability for simply teleporting to a new site and just doing the same thing again. So alpha into S and 1 minus alpha is of course the probability for not following the links. So this makes it irreducible, and then you have the situation where now you can guarantee that Perron-Frobenius theorem would apply, and you are guaranteed that if you do an iteration of the type that we started with, it will actually converge to a invariant probability distribution. So here is okay. So here is that original paper published in 1998. Rest, as they say, is history. So in fact, it's very simple to simulate. There are already many programs out there, but even you can write your own program to do this. Either you write it as a transition probability matrix and find the eigenvalues and eigenvectors, or you treat it as a random walk problem and do it. Either way, you will get the same result. For example, so this is for a small graph of this mathworks.com website, which runs MATLAB, for example. So about 400 websites or so. So what is shown here are the components of that invariant probability vector. So you see that there are these large peaks which imply that they are the ones with higher page ranks. And maybe I should point out that this alpha, it is believed that the value that possibly Google uses is somewhere around 0.85. And physicists, of course, wrote a paper on what happens if you don't use 0.85. So it turns out that if you don't use 0.85 or if you actually go below 0.6 in alpha, it turns out that the peaks that you are seeing here, you won't be able to get a large peak. So what happens is that so you will get something which is approximately all equal. So you won't be able to say that one web page is more important than the other. Okay. So this kind of a situation is actually dealt with in physics, in many body quantum physics. This is a kind of situation what is called a delocalization, as opposed to the kind of eigenvector distribution you see there where there are very strong peaks. They are called localized systems. So there is a very nice analogy between many body quantum physics and this vector, but that's a story for a different time. But nevertheless, the thing is that what they would call as a phase transition in physics literature would be a transition going from something that looks like this to something that has some prominent peaks, but rest are all very small. Then it's easy for you to say that this is an important page, this is an important page, and rest are all noise. But if it is like this, it's a lot more difficult. So which is where that number 0.85, no one knows how they found out, but seems to be something that's useful. Beyond 0.85, I think works up to, yeah, it does work. So I think that this transition number is somewhere between 0.6 and 0.7, where you actually get this. If you go below 0.7, I think it becomes something like this. That's what I remember. That's the result in that paper. Yeah, so MIT is metal insulator transition. It is very closely connected to metallic versus insulator behavior in solid state physics. Okay, that's why the term MIT. Okay. Okay. So anyway, I think at least this part. Let me stop here with this. Okay. Uh, so in the last, like yesterday and today, we've seen this Perron-Frobenius theorem illustrated with many simple examples, and one example of how you can actually use it in really an important problem. So there are many other centrality measures, but I think if you are inspired and would like to look at it, I think there are any number of books and papers which will help you study them in more detail. So now, if you have any questions on these parts, I'll answer. But otherwise, I'll go to a completely different example which I had listed earlier about infection spreading. So in the next maybe half an hour, I'll just take to very quickly go through that, just to give you a feel for what can be done with. So ultimately, that's also a diffusion process. So we started with studying diffusion process. So this is also a diffusion process. So there are many different avatars of diffusion process. PageRank is one, a simple random walk is one, and also the what I'm going to now speak about is also another. Okay, let me just maybe put the question, then we'll see some details. So this was done during the time the lockdown started, and we wrote a project which was fortunately accepted by DST. So the question is the following. So you heard of, by now I think everyone would have known about these SIR models and so on, the compartmental models for spreading of infection. So typically a lot of that is used to predict, like given some initial conditions, how many people are going to be infected in some city or maybe even in the country as a whole. So that is one game. So people, you can write down several variants of these compartmental models, try to include many more effects and do stuff. Instead, what we were asking is not about predicting how many people are going to get infected or how many will die, but more about what is the danger of a city being infected. So in other words, let's say you give an initial condition, something like saying that maybe a city like Delhi has got the first few infection cases. Now you ask the question, if Delhi is the outbreak location, when will say Ahmedabad get it? When will say Chennai get, or any other place in the country? Okay. So that is a question that we ask, and this actually depends not so much on how severe the infection is, but more on the mobilities on the network. So it is actually a network problem. So you have all kinds of transport networks in the country, and even if you have infection in one place, the transport networks basically diffuse it all across. Then you can ask the question, which other city got it first, which got it second, and so on, and give a hazard rank. So the city that gets it first will be ranked 1, but that's with respect to a particular outbreak location. Okay. So that's the whole thing. Okay, so there are all kinds of interesting historical sidelights to this. I'll probably not. And in fact, one of the very beautiful examples of real data that was used actually was from the plague in Bombay. not far from us here. So this was the first paper where they introduced this SIR model, and the data actually came from the plague, which was done by the sanitary inspector in office in Bombay between 1905 and 1907. Okay, to those, this is for like in case you are not seen this model. So this SIR is a compartmental model. So you can think of it as 3 states in the Markov chain kind of language. So you have S, I and R, susceptible, infected and recovered. Recovered means those who have recovered from the disease and those who have even died from the disease. Both are called recovered. So these are the 2 transition rates. So if an infected person comes in contact with a susceptible person, then both are infected. So the susceptible person also gets infected. So that is the first equation with the rate alpha. Okay. I plus S is 2I, and an infected person with some rate alpha over time recovers, which is something that you see anyway, whether through use of medicine or whatever. So finally some people recover. And all that is captured in these 3 nice, simple enough differential equations. Okay. The rate of change of susceptible population, infected population and the recovered population. And since everyone has to fall in one of these 3 compartments, the sum of these 3 should be a constant, which is equal to the total population. Okay. And that is constant all across time. So at any given time, the fraction of people in each of these boxes will be changing, but the sum has to be n, it has to be a constant. So you assume that the total population does not change, which is reasonable over short time frames. At least in India, where the population is so large, it doesn't matter much. Okay, so if you try to solve it, there are 2 possible distinct scenarios that you will get. So there is one case, for instance, you see that left curve at the top, especially look at the red curve, which is the infected case. So you can see that initially it increases, that is that exponential increase of number of infected people. That is the worst case scenario that we met during COVID times. There are times when the number of infections keep increasing, and that happens provided your R0, the parameter that depends on alpha and beta is greater than 1, or what is called the reproduction rate. But if your R0, which depends on alpha and beta, is less than 1, you can see that the number of infected cases, this one, the brown curve at the bottom, it actually just decreases, goes to 0. Okay. So that's a happy scenario where infections are reducing. So typically, you would have seen during the COVID time people quoting this R0 number, saying that it's now getting lesser than 1 and maybe happy times are ahead and so on. So anyway, so these are 2 distinct possible solutions that you can get. Okay, so I'll probably not do other these things. Okay, this is basically saying that this SIR model would work, let's say, for one particular city, something like this, where you have a well-mixed population. Basically, it assumes that everyone gets in contact with every other person. Okay, so that happens only if you're in a large country like India. It's not true for the entire country, but maybe in small areas it works. So if you have to apply SIR model, one instance of a SIR model in a country like India, it will hold good for maybe some locality or something approximately. So what happens if you have multiple cities like this? So you have, let's say, 3 cities, but in general you can have, so each of them you can treat as a node, and in each city you can apply this SIR model. And you have different numbers of population. So if you consider cities with large population in India, it will range from few lakhs to big cities like Bombay, Delhi, Chennai, exceeding 1 crore. Okay, so now you can reframe the question in terms of a network like this. So the basic idea is that irrespective of how severe the infection itself is, which is a biological problem maybe, but the spread of infection is caused by mobility of people through transportation networks. So you can ask the question like this: if I have a network of n cities or towns, and so those n cities and towns are indicated by x1, x2 up to xn, and if the outbreak location is given as x1, for example, can a hazard value be assigned to all other cities and towns, which reflects the risk of them getting the infection. So again, this is not about predicting the case load and so on. Okay, so which means that apart from the standard SIR model, we need some set of dynamical equation to account for people going from one city to another city, and which is the core contribution that we did. Essentially take into account, you write some probabilities for people going from city A to city B. And now if you see this set of equations, so at least the left hand side you see that you have dou S by dou T, dou I by dou T, dou R by dou T, which looks somewhat similar to the SIR model, and N there is an index for the cities. Now this equation actually has these two parts. The first part within that blue box is simply the standard SIR equation, no change at all. But in addition, we have augmented that with this other boxes in brown, which actually takes into account the movement of people from one city to other. So you have M of those cities. So there is a SIR model and there is mobility information which is incorporated in that. So N and M that you see everywhere in the summation and so on is simply the index for cities. Okay, so there are 1, 2, 3 up to M cities. So this is how the whole thing works. So you have SIR model, very well known model for almost 100 years or more, and then you need the mobility data, and if you want to apply it to a real situation, you need population of each city, you need also how many people are moving from one city to another city. So the population data for us comes from the census data, and we actually integrated a whole lot of mobility using the rail, road and air traffic data. Okay. So that's how the mobility data comes from, and all this is fed into this, this set of equations, and then we calculate what is called an effective distance. I will come to that in a moment, and finally create a hazard map. So the key idea here is the effective distance between any two cities. There is a geographical distance, say between Bombay and Ahmedabad and so on. There is some number that's given as the geographical distance between city A and city B. But this effective distance actually takes into account how many people are traveling between these two cities. The idea here is that this P that you see is simply the probability, conditional probability that a person who is leaving city I actually goes to city J. If there are more people going from I to, let's say for example, no one ever goes from I to J. In that case, effective distance is 0. Okay. So which means that in this metric, if no one ever goes from A to B, then there is no question that infection would spread, even though they may even be nearer geographically. On the other hand, if there are more people traveling, you are going to get some non-zero number for the effective distance. So that is the intuition behind creating this metric, and that metric depends on people moving, so that Fi and Fij are drawn from the mobility data. Okay, so F and Fij are simply this, where is it? Yeah, it's essentially the number of, this one. So Fij is the number of people going from city M to city N. Fm is total outflux from a city. So what you see as Pij is this, the fraction of people going from one city to the other. Okay, the central result is uh, the time of arrival, meaning time of arrival of the infection. So here, keep in mind that you have already declared one city as the outbreak location. Okay, that is fixed. That is part of your initial condition for the problem that is given. And then you are asking what is the time of arrival at all other maybe towns and cities, and this time of arrival is proportional to this effective distance. So that is the central result. And okay, so this is the kind of data that we used. So we, from the census data of 2011, we used 446 cities which have a population of more than 1 lakh. And so we used all the available data of train, air traffic and road traffic. And for train, for example, that 446 cities actually boils down to 435, because some cities are like Hyderabad and Secunderabad are treated to be the same, and so on. And of course, there are many different sources from which the data is taken. That is what you see here. And these red dots in the map is essentially those 446 cities. And okay, so from all the data that we computed, this is a summary statistics of mobility. Okay, so from a network perspective, what you need to see is that the number of nodes is 446 and number of edges is 46,000. So it's hugely redundant nodes are there. Clearly, you need that for travel purposes. But it also tells you a few other interesting facts, like for example, railways continue to be the main mode of people's transport in India, and airway, most of us may be traveling in flight, but that's really still a small percentage. And okay, so this is basically showing the entire data in terms of a network. Maybe it doesn't look very good here, but the thickness of the line that you see is proportional to how important, it's a weighted graph basically. So the thickness basically tells you the weight of the link. So for example, if you see Bombay to Delhi, it's drawn with a very thick red line. That's simply because it's one of the trunk lines in the country, both in terms of number of flights and trains that go between the two stations. And all the local trains have been removed. Like for instance, both Chennai and Bombay have a huge local train traffic. They have been removed from this data. So here only top 500 connections are shown. Okay, so this is the result. So for example, now let's say you declare the outbreak location to be Delhi. In that case, you can ask the question. So I said the central result is that time of arrival is proportional to the effective distance. In fact, that's what you see. So before you see the left side graph, see the right side one here. Here, this, okay. So this one. So if I actually plot the time of arrival versus the geographical distance between the cities, you see that there is no correlation at all. It's just a jumbled collection of points. But instead, if I use time of arrival on the x-axis versus the effective distance on the y-axis, you see that it all falls nicely on a straight line. Okay. So which means that time of arrival is directly proportional to the effective distance. So now you can choose any outbreak location you want. So for example, a small city like Tirupati is chosen as outbreak location. So rest of the 434 cities in terms of the effective distance fall in a straight line. But again, if you actually see it in terms of the geographical distance between them, again it's a jumbled collection of points. So again, you can try it. It's the same result. You can try it with any outbreak location. Ahmednagar is a very small town in Maharashtra. Bhopal, Chennai, Pathankot, whatever. Okay, so so the interesting thing is that, so once you have these time of arrival, you can rank them. Okay, that is what is done here. Maybe let me. So for example, what it shows here is, like for example, the leftmost one, it says that Patna is the outbreak location. Then from the data, you ask the question, which are the top 10 cities that are most likely to be infected if Patna is the first outbreak location. So that is what you get. And the TOA is time of arrival. So if Patna is affected, place like Gaya would get it in 2 days approximately, and so on. Delhi would get it in again close to 3 days, and so on. So then you can give a rank 1, 2, 3, 4, 5, and that would be the top 10. If, for instance, Bombay is the outbreak location, you can see that place like Thane, Pune, and so on, which are somewhat closer, but there is also a large flux of people traveling between these two. They would be the ones to be affected. You can also see another point here. So let's say if Tirupati is the outbreak location, Bangalore is actually very close to Tirupati. Very close meaning closer than Bombay. But you see, it takes 5 days for infection from Tirupati to reach Bangalore. But on the other hand, from Bombay to Bangalore, it reaches only in 2 days. That's simply the effect of the flux of people, number of people traveling. Okay, I'll try and show you this website. Okay, so actually, so we created a website where you can choose the, unfortunately, India map should appear here in this place, it doesn't, but still you can go and choose any city, any of those 435 cities that I said as an outbreak location. So for instance, let me put Ahmedabad, and it will actually give you, yeah, unfortunately that you can see a rough outline of an India map there, but that's gone. I'll try and fix it later, but you can see that the size of the red circles is higher the hazard, higher is the size of, I mean larger is the radius of that circle, but you can see the list here, the top 10 list. So if Ahmedabad were the, yeah, if Ahmedabad were the outbreak location, so these would be the top 10 cities to be affected. Now you can go back and let's say I can choose, for instance, Delhi. If I put Delhi as the outbreak location, yeah, so these would be the top 10 cities to be affected. So you can keep doing this. You can maybe choose Rohtak if you like. Okay, so you can keep playing with this. But anyway, so again, all I wanted to say is that here again, what I did not discuss is there is quite a bit of interesting diffusion problem here. In fact, there are very well-known diffusion equations that have been studied which actually corresponds to the kind of diffusion that we saw in this, but that's a story for another day. But in any case, I think it's another interesting application of both random walks and diffusion equations. Okay. Okay, I think I'll stop here with this, and if you have any questions, you can ask me now, and also I'm going to be here until lunchtime.